very good morning to one and all. Today we are going to see about hydrothermal scheduling. So if you see this figure, this figure consists of two-unit hydrothermal system. So why we are going for this hydrothermal scheduling? There are many sources of energy like hydro, thermal, then non-renewable energy resources, then your power generation from gas power plant, like that nuclear power plant, like that many sources of energy is there. But this two, like hydro and thermal, that is steam power generating units, are very common, very common. Like in the peak hours, if the hydro reserves are very less, then we have to rely on this steam powered generating unit. Like hydro, hydro is less costly. That is, no money is needed, no fuel cost is needed for generating the power. Whereas steam, you need the coal resources for generating the steam power generating unit. Suppose we have two sources of electrical energy to supply a load, that is hydro and thermal. That is, one is hydro and another is steam power generating unit. The hydro power plant can supply the load by itself for a limited time, that is for any period of time j. The hydro power plant can supply the load by itself for some limited time, say 8 hours, say 6 hours, depends on the amount of the water that is being in the dam. So hydro, if you see hydro can supply the load by itself for a limited period of time. So for time period j, where j is equal to 1 to j maximum. The time period may be of 1 hour to maximum of 8 hours. Say for example, here the hydro might be available for 8 hours. So 1 to j maximum. Here P of Hj maximum, P of Hj, that is power generated from hydro maximum, is greater than or equal to P load. So we are considering the power generation generated from the hydro itself. The maximum generation is being generated so that it can satisfy the load. That is, PHJ maximum is greater than or equal to P load of J. When compared to the load, the power generated from the hydro alone, the maximum power generated from the hydro alone is greater than or equal to the P load of J. P load of J. That is, J is equal to 1 to J maximum. J is equal to 1 to J maximum. However, the energy available from the hydro plant is insufficient to meet out the load. So, the energy available from the hydro plant alone is insufficient to meet out the load. Why? Because, as I said, like up to 8 hours or 10 hours or 12 hours only, like based on the resources, we are going for this power generation from the hydro. Because once the water is utilized, water is opened from the hydro power plant, it has to be utilized for both in the sense for power generation, for generating the power, and as well as the agriculture power purpose also. So once the water is being open, it might be utilized for the both the power generation as well as the agriculture. And here if you see, like sigma j is equal to 1 to j maximum, phj into nj. PHJ into NJ is less than or equal to sigma J is equal to J maximum P load into NJ. So previously what we consider? Previously we considered power generated from hydro power plant alone. That is maximum power generated from hydro power plant alone is greater than or equal to P load. Okay, P load of J, where J is equal to J maximum. Now, the energy available from the hydro power plant alone is insufficient to meet out the load. That is true, because only if we rely on power generation from hydro alone for 24 hours, it is not possible. Not possible in the sense for 24 hours, even though the installed capacity is there, even though the power generation is there, so it can't meet this can't able to meet out the total power demand. Only up to 30 percentage 40 percentage it can meet out, but majority of the power generation is from the thermal power plant only, something from nuclear. So the power generated from the hydropower plant alone can't able to manage insufficient to meet out the total demand. That is sigma I is equal to J is equal to 1 to J maximum. That is PH of PHJ into NJ is less than or equal to P load of J into NJ. P load of J into Nj, where Nj is nothing but number of hours in a period J. Number of hours in a period J. So period in a J, say for example J maximum we are taking as 8 hours. So how many number of hours in period J na? So 1 to 8, that is number of hours means 8 hours. 8 hours. So the period J, what is the number of hours? Say period we have taken as particular one period of hydropower plant, like that we have taken. So from that particular period of hydropower plant, so number of hours is 8 hours. Here we consider as 8 hours. Example, we consider as 8 hours. So here PHJ into NJ is less than or equal to P load J into NJ, where J is nothing but 1 to J maximum. J is equal to 1 to J maximum. Next, here NJ is nothing but T maximum. NJ, that is number of hours in a period J is nothing but T maximum, where J is equal to 1 to J maximum. NJ is nothing but T maximum, that is total interval, that is total in period of time or total interval. So that is nothing but total interval. So we would like to use up the entire amount of energy from the hydropower plant in such a way that cost of the running of steam plant is minimized. Our ultimate aim is to minimize the cost of the steam power plant. Why? Because if we minimize the cost of the steam power plant, then the whole amount of power generation, that is amount of power generation, might be decreased. Our ultimate aim is to decrease the amount of power generation. If you are spending for 24 hours, say for example for generating 100 megawatt or generating 500 megawatt, we are going to spend 1 crore rupees. Our ultimate as a whole amount is 1 crore rupees for generating alone by using power coal resources. So what we are doing is we are reducing the amount of coal coal spent to some 50 lakhs rupees. We are reducing. So rest of the power generation we are managing with hydro power station. So ultimately 50 lakhs is being reduced out of 1 crore. So 50 lakhs, if it is reduced, not defaultly the profit to the generating station that is generation corporation, might be increasing. Meanwhile, if the profit is increasing means, meanwhile it will be reflecting on the tariff. What we paid will be decreased. So whatever the amount we will pay for the tariff might be decreasing. So we would like to use up the entire amount of energy from the hydro power plant in such a way that the cost of the running the steam power plant should be minimized. So our ultimate aim should be cost from the running cost of the steam power plant should be minimized, so that rest maximum amount we have to utilize from the hydro power plant. The steam power plant plant energy required is given by P load, that is steam plus hydro. Steam plus hydro is equal to the load. Okay, so whatever the power generated from the steam energy plus whatever the power generated from the hydro energy is nothing but load. That is steam energy plus hydro energy is equal to load energy. But here our ultimate aim is to minimize the running cost of the steam power plant. So what we are doing is we are taking out the steam power generated from the steam power plant alone. Energy, so not power, energy generated from the steam power plant alone. So steam energy is nothing but load energy minus hydro energy. So load energy is nothing but sigma j is equal to 1 to j maximum P load j into Nj minus sigma j is equal to 1 to j maximum Phj into Nj, where Nj is nothing but number of hours in a period j. Number of hours in a period j. Number of hours in a period j. So particular period of time, if we consider now how many number of hours that particular hydro power plant is operating, or steam power plant is operating, will not require the steam unit to run for the entire interval of T maximum hours. Will not require the steam unit to run for entire interval of T maximum hours. Therefore, PSJ into NJ, PSJ into NJ, that is the steam energy. Steam energy is nothing but PSJ into NJ, that is nothing but capital E. So capital E is nothing but PSJ into NJ. So here we will not require the steam unit to run for the entire interval of T maximum hours. Okay, where ns is nothing but number of periods of steam power plant to be operated. So number of period of steam power plant to be operated is nothing but ns. So j is equal to 1 to ns. So number of period of time so that steam power plant is operated. So that is nothing but ns. So here E is nothing but Psj into Nj. Then sigma j is equal to 1 to ns of Nj is less than or equal to T maximum. That is number of period of time where steam power plant is operating is less than or equal to T maximum hours. That is for the entire period of the time. Generally it should be less than only. If it is equal, then maximum amount of power generated from the energy generated from the steam power plant is equal to T maximum hours. That is that scenario will not appear. If that scenario will happen means the cost required for a steam power plant will be very higher. So n j is equal to 1 to ns, that is nj is less than or equal to T maximum hours. Next, the scheduling problem becomes mainly our scheduling problem becomes minimize the total fuel cost. How to minimize that is even in our economic load dispatch also we have to minimize the total fuel cost. Total fuel cost here particularly in hydrothermal scheduling. So what is our main objective function? Our main objective function is to minimize the total fuel cost. Particularly, we have to minimize the power generated from the steam generating plant alone. That is energy generated from the steam power plant alone. So energy generated, what is the energy generated here? PSJ into NJ, where J is nothing but 1 to NS. That is number of period of time where the steam power plant is operated. So we have to minimize the total energy, that is total fuel cost, and multiplied by the number of hours, that is energy generated from the steam power plant alone. So what is the objective function? Here the main objective function is to minimize the total total energy generated from the steam power plant alone. So how much hours that power plant is running is nothing but J is equal to 1 to Ns. That is number of Ns is nothing but number of periods that steam power plant is operated, subject to constraints. So any problem, any optimization problem has one objective function as well as the constraints. So one objective function as well as the constraint, as I said. So what is the student's objective function? Student's objective function is to get the maximum marks. So here in hydrothermal scheduling, we have to minimize the, that is power generated to the steam power plant. Whereas generally, what is our majority of the students' objective function is to get the maximum marks, that is maximum CGPA or maximum percentage. What are their constraints? Constraints is nothing but they have to study only for, in a day they have to study only for 2 hours a day. 2 hours a day. Only for 2 hours a day, they have to get the maximum percentage. They have to get more than 90 percentage of marks. They have to get more than 9 CGPA above. So that is a major objective function of students, a majority of the students. Similarly, like here, the objective function of the this hydrothermal scheduling is to minimize the power generating from steam power plant, subject to constraints. Subject to constraints, here what we have taken is constraints. So PSJ into NJ minus E is equal to 0. We have taken as PSJ into NJ minus E is equal to 0. Here from this equation, PSJ Nj minus E is equal to 0. So here, if you see this figure number 5.9, yeah, figure number 5.9. This is the here if you see, this is the load axis. This is the time axis, number of period of time that particularly this steam and hydro is operating. So when we combining this steam and hydro power plant, when we combining this hydrothermal scheduling, if you see here, maximum power generation, that is happened from the hydro power plant only. Maximum power generation that is happened from the hydro power plant only. When compared to the steam power plant, the maximum power generation happened from the hydro power plant only. Why? Because if we reduce the power generation from the steam power plant, automatically our the cost might be reducing. So that is also number of operating hours, number of operating power generation versus power load. That is, load is nothing but the demand is nothing but the power generation, whatever the power generation, that is equal to the demand. So some losses are also there, but we have not taken the losses. So whatever the power generation from the steam power plant, for a particular period of time. So here if you take T maximum hours for 24 hours, say for example 24 hours in a day, what we are doing is maximum power, that is around 12 hours of power we are generating by, sorry, not 12 hours, maximum more than 12 hours, 16 hours of power we are generating by hydro power plant alone. So like rest of the power if you take like eight so 16 hours plus 8 hours, 8 hours is being generated by steam power plant alone. So if you come to the practical scenario, again, some other renewable energy resource also added over here to the hydro. So hydro plus renewable energy resources like PV, like solar power generation, and as well as wind energy conversion system. So that also added here, and also some biogas power plant. Something that also will be added here, and steam power plant alone. So our ultimate aim is to reduce the power plant, reduce the cost of the power generation. So ultimately, what if you reduce the power generation from steam power plant, automatically the total amount what we spent will might be reduced. So here only steam and hydro alone taken. So maximum power generation that to be happened only by hydro power plant alone we have taken into account. So next step we had objective function as well as the constraints. So what is the next step? We have to form the Lagrange's function. So what is the Lagrange's function? Lagrange's function is nothing but objective function plus some constant into constraints. Lagrange's function is nothing but objective function plus some constant into constraint. I think you have studied this Lagrange's function at your mathematics 3 numerical methods, I think. So in the numerical methods of solving the like mathematics, you might have studied this Lagrange's function. So Lagrange's function is nothing but objective function plus some constant into constraints. So what is the objective function? So here the objective function is, what is the major objective function? Yeah, major objective function is minimize the total fuel cost. That is sigma j is equal to 1 to ns f of psj into nj. So what is the constraints? This psj nj minus e is equal to 0. So here we have taken. So objective function plus constant. Here alpha we have taken as constant. Alpha we have taken as constant into constraint. So objective function plus some constant alpha into constraint. So next, what is the further step? We have to differentiate and equate it to 0. As similarly, what we did in economic load dispatch problem. So we are differentiating this Lagrange's function with respect to PSJ. So here our ultimate aim is to reduce this power generation from the PSJ, that is steam power generating unit. So dou L divided by dou PSJ is equal to 0. So differentiating this Lagrange's function with respect to PSJ, that is equating it to 0. So here what we are doing is we are differentiating this df of PSJ divided by the PSJ, that is dou L divided by dou PSJ is equal to 0. So while differentiating here we have taken as E minus sigma j is equal to 1 to ns PSJ into nj. Similarly, as we did it in like economic load dispatch, that is energy, the whole energy, steam energy generated from the steam energy generated is greater than, we have considered greater than the PSJ into NJ. So here we have taken as E minus sigma j is equal to 1 to ns into PSJ into NJ is equal to 0. So while differentiating, so we'll get like this. While differentiating, we'll get, So if we differentiate with respect to PSJ, so this term will be become, I think this term will become -1. Okay, this term will become this capital E will be neglecting because it is greater than this term. So this E term we are neglecting. So while differentiating this term, we will get -1. So -1, that is PSJ is equal to -1. So into alpha is nothing but minus alpha. So df of PSJ divided by dPSJ minus alpha is equal to 0, where J is nothing but 1 to ns. N is nothing but number of hours where number of hour period of time for steam power generating unit. So that is nothing but df of PSJ divided by dPSJ is equal to alpha. So equal to alpha. So here minus alpha is equal to 0. This is equal to alpha for J is 1 to ns. This means that the steam power plant should be run at constant incremental cost for entire period it is on. For the entire period it is on. So steam power plant should be run at constant incremental cost for entire period it is on. Let this optimum value of steam power generated be PS star. So this is the from this figure, this is the optimum value of the power generated from the steam power plant. So this we have taken as PS star instead of PS. This PS star is nothing but optimum value of power generated from the steam power plant. So that we are taking as PS star. So optimum value of steam power generated to be the PS star, which is same for all the interval of time where the steam unit is on, which is same for all the interval of time where the steam is on. Next, this type of scheduling is shown in the figure 5.9. We have already seen the total cost over the interval. The total cost over the interval is, that is nothing but FT, that is total fuel cost. Total fuel cost is nothing but sigma J is equal to 1 to ns. F of PS star into Nj is nothing but F of PS star. Okay, so this term we have taken outside. So that is F of PS star alone. That is that is the fuel cost of this optimum power generation from steam power plant alone we have taken outside. Then this is sigma J is equal to 1 to ns into ns nj. So this alone we have taken outside. So this is nothing but f of ps star into ts, where sigma j is equal to 1 to ns into nj is nothing but ts. We have already we have seen from the previous equation here. Yeah. So sigma j is equal to 1 to j maximum into nj is nothing but t maximum. So similarly, this we have taken as ts. So sigma j is equal to 1 to ns into nj is equal to ts. That is total period of time from the steam generating unit. So here it is shown now. So where ts is nothing but sigma j is equal to 1 to ns into nj. That is total runtime for the steam power plant. This is nothing but total runtime for the steam power plant. So let the steam power plant fuel cost function, the fuel cost function is given as f of ps is nothing but a plus ps b into ps plus c into ps square. So but in economic load dispatch we have taken like ps square plus b ps plus c. Like that also you can take, like that fuel cost function also you can take. So no problem in that. So here we have taken like this. So that is also no problem. See here in this in this material it is taken as like this. You can also take like this, no problem with that. So let the steam power plant cost will be expressed as F of PS is equal to A plus B PS plus C PS square. So next, coming to the total fuel cost. Total fuel cost is nothing but, so here total fuel cost is nothing but Ft is nothing but F of Ps star into Ts. So F of Ps we have taken. So total fuel cost is nothing but this F of Ps into Ts. So A plus B into Ps squared plus C into Ps star square. Okay, so into Ts. So that is nothing but total fuel cost, total fuel cost Ft. So here sigma j is equal to ns up to ns ps j into nj. Ps j into nj is equal to sigma j is equal to 1 to ns into ps star into nj. Ps star into nj, that is nothing but ps star into ts. Ps star into ts, that is nothing but e. So from the previous notation here, so if you take sigma j is equal to ns, ps j into nj is nothing but ps star, that is optimum amount of power generated from the steam generating unit, that is nothing but ps star into nj, that is equal to ps star into, this is nothing but ts, already we have seen nj is nothing but ts. Sigma j is up to ns into nj is nothing but ts, that is nothing but e, that is nothing but the total energy generated from steam power plant, that is nothing but capital E. So here ts is equal to e divided by ps star. So if you take like this, ES, this two terms, so TS is nothing but E divided by PS star, that is the time interval, time interval for the particular steam power plant is nothing but energy generated divided by optimum power generated from the steam power plant, that is TS is equal to E divided by PS star. So here if you take FT, total power generation, okay, total power generation is nothing but A plus B PS star plus C into PS star squared into E divided by PS star from this equation. From this equation, that is Ft is equal to A plus, so we have to substitute Ts. So Ts here, Ts in this equation. So Ts we have already calculated, that is E divided by PS star. So Ft is nothing but A plus BPS plus star plus C into PS star squared into E divided by PS star. So Ft is nothing but, so A divided by PS BPS star plus C into PS star squared into E divided by PS star. So now we can establish the value of PS star by minimizing the total fuel cost. So for this, what we are doing is we are differentiating the total fuel cost with respect to PS star. PS star, that is nothing but optimal power generated from steam power generating unit with respect to PS star. Okay, then we are equating it to 0. So by differentiating this term we are and equating it to 0, so finally if you differentiate it, you will be given like the final equation will be like minus ae divided by ps star square plus ce is equal to 0, that is minus ae divided by ps star square plus ce is equal to 0. So from this while calculating from this, PS star is equal to root of A divided by C. From this again further simplifying, PS star is equal to root of A divided by C, which means that the unit should be operated at its maximum efficiency point long enough to supply the energy needed, that is E. So PS star is nothing but root of A divided by C. Root of A divided by C. So coming to the heat generated. So heat generated also here we have taken into the account. So the fuel cost into heat generated is nothing but the total fuel cost. Okay, so heat generated into fuel cost is nothing but the total fuel cost function. That is the fuel cost function. That is the fuel cost into heat generated in the power. That is power generated in the steam power generating. So heat generated in the steam power generating unit into the fuel cost is nothing but the the fuel cost function, that is f of ps, f of ps, that is nothing but a plus b into ps plus c into ps square. So whereas fc is nothing but fuel cost, then the heat rate is given by h of ps into ps divided by ps is equal to like same like that from this equation 1 divided by fc into a divided by ps plus b plus c into ps from this equation. So if the heat rate has to be minimum, heat rate has to be minimum. Similarly, like that, fuel cost has to be minimum. So heat rate also can should be minimum. That is, so what we have to do is we have to differentiate with respect to we have to differentiate this term with respect to ps and equate it to 0. So while differentiating this term, that is h of ps divided by ps with respect to 0, so finally we will get minus a divided by ps square plus c, minus a divided by ps square plus c, which gives the best efficiency at ps is equal to root of a divided by c. So further simplifying, so taking outside ps outside, so we'll get a divided by c. So that is nothing but ps squared is equal to a divided by c. So ps is equal to root of a divided by c. It's nothing but ps star, that is optimum power generated from steam generating unit. So heat generating unit also we are given with the best efficiency of, that is root of a divided by c. Whereas from the fuel cost also we are giving we are that is giving the best efficiency, while root of a divided by c, that is optimum power generated from this steam generating units. So our ultimate aim is to reduce the, that is reduce the power generated from the ultimate aim is to optimize the power generated from the steam generating units. That is the optimum power generated from the steam generating units we have taken as ps star from the whole period of time, that is T maximum hours. So this is the hydropower hydrothermal scheduling. Thank you everyone.